math. You're all probably dreading this lecture, but math is actually very important for computer graphics because we are using, well, computers, and what the computers do, they compute. So we need to give them math to compute, and this is how we represent like computer graphics, different 3D shapes, objects, and we'll see what tools and what math will we actually need for computer graphics. The most important things are points and vectors. So you probably all have drawn this Euclidean coordinate system at some point. So there's an origin, there's an x-axis, there's a y-axis. In computer graphics, we distinguish points, which are kind of locations in space. In Estonian, they're also called kohavektor. So those specify different locations. So we have this location here, 7.2, 2.3. But we also have things like vectors. So vectors are kind of directions in space. Also in Estonian, they're suunavektor. So we can have this vector v, 0.8, 1.4, and if you think about this direction in this particular arrangement, it doesn't really have like an origin. So it's this direction vector, and it could be anywhere. So all these v's here are basically the same vector. But this u that is pointing in a different direction, well, is not. Both these points and vectors are elements of, well, a 2D, 3D, or even a 4D dimensional vector space. We'll see where this 4D comes in a bit later. But if we're talking about 2D or 3D computer graphics, then the points and vectors are elements of 2 and 3 dimensional vector spaces over the field of real numbers. So we're always talking about like these vectors that have real number coordinates, or points that have real number coordinates. In linear algebra, you could have a vector space over different fields as well, but here we'll try to keep things simple. More precisely, we could say that they're elements of a coordinate space, because these elements have coordinates, so an x coordinate, y coordinate, and z coordinate. So both are kind of vectors in terms of algebra. But as we see soon, some operations will make sense for points and some will make sense for vectors. And a space that actually contains both of them and defines an addition between a point and a vector is called an affine space. And it kind of makes sense. So we have a location, we have some kind of a direction vector, and maybe you have even done this in high school. You add the direction vector to your location and you get to another location. So A plus some kind of a vector v is this point B, or takes you from A to B. And this is actually your everyday Euclidean space. There's no non-Euclidean trickery here yet. So more precisely, we could call this an Euclidean space. And we can also think about like different vector spaces. So taking a step back again, we can think about like a vector space of points. So all these locations and these location vectors define like a vector space of points. And then we can think about like a vector space of vectors. So all these vectors here that would now be fixed to some origin. It's not the same origin that's there. It's a different space that would be like a vector space of vectors if you want to imagine these two spaces separate. And maybe you have learned this definition already, that given a vector space over, let's say, a two-dimensional field of real numbers with a basis and the origin, the elements of the vector space can be represented as a linear combination of the basis vectors. Now, these are all important terms here, and in computer graphics we'll use them a lot. So we have a basis, we have an origin, and this vector that we have, this v, this v3, 2, and this 3, 2, all that they denote are the coefficients in the linear combination of the basis vectors. So if you would take 3 times this basis vector x, so 1, 2, and 3, and add to it 2 times the basis vector y, so we're over here and we add y and another y, then we would end up at this v coordinate. And this is all that these vectors are. They're a linear combination of the basis vectors. And in Estonian there is this interesting term called reeper. So sometimes if you want to like say the basis and the origin together, like this set of a basis plus the origin, then in Estonian there is this word reper. I don't know an English corresponding word for that. And here's a formula. So this vector v is gonna be some coefficient times the first basis vector. So this 1, 0, this is like 1 in x, 0 in y. So this is this first basis vector plus some coefficient times the second basis vector, and this is that one. And these coefficients, well, these are the coordinates. And in this particular case, alpha would be 3 and beta would be 2. Now we can also talk about like a coordinate space. So all the elements of our vector space are kind of these n tuples. Then we can call it the coordinate space. 2D we have 2 coordinates. In 3D we would have 3 coordinates, and so on. So we could call it the coordinate space. Now if we put those two spaces together, so we have on the left this coordinate space of points and coordinate space of vectors. And now we put them together in this way that we define an addition between a point and a vector. So the example we had before, like point A plus some vector v would give us point B, and then that will give us an affine space. So it's kind of this mathematical construct where we have two vector spaces kind of put together in a way where there's an addition between the elements of the first and the elements of the second vector space. Now let's look at what happens if we combine those points and vectors in interesting ways. For example, we could create a line. So a line, we would need 2 points that the line passes. So if you have these 2 points, we could draw a line, like we could physically draw a line between them. But we'll see soon that we can also mathematically define this line. Or if we want to make a line and we don't have 2 points, but we have 1 point and a direction vector, then that would also give us a line. Because you can like take a point, and if you have a ruler, you point it towards the direction vector and you can draw a line. Now, how to mathematically do that? So in the first case, we could define this parametric equation, and it's parametric because we have this one parameter and we put in real numbers into this parameter, and this will give us points on the object. So in this case a line, and if we define it like that the coefficient for A would be 1 minus alpha and the coefficient for B would be just alpha, or parameter, then we will get points on the line if we put real numbers in there. And you can think about, like, if you put in 0, what happens? You get 1 A plus 0 B, so you're at A. If you put 1 in, then you get 0 A plus 1 B, you're at B. And let's say you put in 0.5, then you're 0.5 times A plus 0.5 times B, and you end up in the middle of those 2 points. And you can put in all sorts of different values here and get the whole line that way. Now why this is useful is because this allows you to define any line and generate points on that line. But let's see the second example as well. So here we are using the direction vector, and we have this point A and we have this direction vector D. And if we define this equation now like this, that line alpha equals A plus alpha times D, then we can also get all the points on the line. And this D, well, this is actually just B minus A. So if you take 2 points and you want to know the vector between them, then you just subtract those 2 points and you get the vector between those 2 points. And if you would plug in like B minus A over here instead of D, then you would get back the original equation that we had before. But here you can test out a similar thing. So if you put 0 here, you would be at A. If you put 1 here, you would be at the end of this D. And basically, it's this point A plus some coefficient times this vector. So however much you take this vector, you get all the points on the line. If you take this vector with a negative coefficient, you would get the points on the opposite side of A, but still on the line, on the same direction. One trick that people also do here is that they normalize this direction vector. So instead of having just like an arbitrary length of this vector, it's sometimes useful to normalize it because we only care about the direction. The magnitude comes from this parameter. So what number we put there, that's how far along the line are we. But it kind of would make sense that if we, let's say, put 1 in there, then we would be 1 unit away from the point A. So often people normalize this vector, and this just means, this normalization just means that you take your vector and you divide it by its length. If you divide every coordinate with its length, then you will get out a vector that has the same direction but length 1. Now we can take this thing a step further. So there are a couple of more definitions. So let's say we have 3 points. We have A, B, and C. And we want to like find all the points that are inside this triangle. Or we could even say that we want to find all the points that are on the same plane as this triangle if we're in 3D. And this is where something called a convex combination comes into play. So the coefficients of a convex combination of the vertices are the pericentric coordinates of the points in the triangle. So what does this mean? This means that if we take this equation, and this is very similar to what we had before. So before we had this line, we had this 1 minus alpha and alpha, but now we have alpha, beta, and gamma as coefficients for vertices A, B, and C of this triangle. And if we now constrain those 3 coefficients with these constraints, that their sum needs to equal 1, and all of them are non-negative, then this combination here is a convex combination. So you have probably learned about like a linear combination where the result is like a multiple of the first value plus multiple of the second value plus multiple of the third value. So it's very similar, except that these multiples, these coefficients, are constrained by these 2 constraints. And it turns out that if we now put different numbers into these coefficients that satisfy these constraints, then we actually get all the points inside this triangle. And this is called this convex combination. Now these coordinates, these coefficients, alpha, beta, and gamma, they're actually coordinates. They're called pericentric coordinates in relation to these 3 vertices. So let's say we want to have the result as A. So what would be the coefficients here that this equation would give us A, this point A? And if you think about it, well, it's just 1, 0, 0. So a triplet 1, 0, 0 would be the pericentric coordinates of point A for that triangle. And we could have like, let's say point B, it would be 0, 1, 0, point C would be 0, 0, 1. So these are the pericentric coordinates. And we could have like 0.5, 0.5, 0. So that would be a point between somewhere on this line. And if it's 0.5, then it's exactly in the middle. So C was 0 and we have 0.5, 0.5. So it's in the middle here. So the pericentric coordinates of a point in the middle of this edge would be 0.5, 0.5, and 0. And this is useful because some of the algorithms in computer graphics kind of use these coordinates. And by using these coordinates, it makes the math somewhat simpler. Now, what about combining vectors and vectors? So there are operations that we can also do between different vectors. First, normalization. So we already talked about normalization. So this is just that if we have a vector v, we want to make it smaller or maybe larger. We want to make it such that its length would be 1, but direction would be the same. So vectors have a direction and a magnitude, or we could call it length. And very often in computer graphics, we don't care about the magnitude, we just care about the direction. So, and the math will become much simpler if we make the magnitude or the length of the vector 1. And to do that, well, we just divide the vector with its length. In Estonian, it's called normaliseerimine. Another useful operation we can do is the dot product. In Estonian, it's called skalaarkorrutis, so a lot of you probably know it by that name. And this turns out to be an extremely useful operation in computer graphics. And why? Because it has two definitions. So it has this one geometric definition, which is just the length of the first vector, the length of the second vector, times the cosine of the angle between those two vectors. And it also has this algebraic definition, where it equals like the first coordinate of the first vector times the first coordinate of the second vector, plus the second coordinate of the first vector, plus the second coordinate of the second vector, plus the third coordinate of the first vector, plus the third coordinate of the second vector. So if we have these vectors with coordinates, which we usually do in computer graphics because we define them with coordinates, so our wind blows that way, and this is like 3 units in x and 2 units in y, and this is our direction. And if we have these vectors with coordinates, it's really easy to calculate this bottom definition. But where this actually comes very useful is that we need to very often in different algorithms, and we'll see these algorithms in a couple of weeks, we need to know the cosine of the angle between two vectors. You have a direction this way and a direction that way, then the cosine of the angle between them becomes something that we want to find. And this is where this dot product is very useful, because if we have these normalized vectors, so both the lengths of both of these vectors are 1, then we can just take the dot product between them to get the cosine of the angle. And it becomes easier when you see the different uses of it, but for now just remember that this dot product is very useful in computer graphics. It's also sometimes called scalar product or inner product. Another useful operation is cross product. It's not that useful then as the dot product, but sometimes we want to use a cross product as well. So the cross product gives a vector that's orthogonal to the operand vectors. It also has two definitions, and we're not going to go too much into these, and you've probably learned them in your high school math class. But if you have two vectors and you take the cross product, then the result will be another vector that's kind of orthogonal to the initial two. And we'll see soon like which way is it pointing, because you have two choices. It could be orthogonal this way, pointing upwards, or pointing downwards. But we'll see how to detect this. This is also called vector product, and in Estonian vector korrutis. One note here that in computer graphics we really like the terms dot product and cross product, because with the dot product we want to put a dot between the vectors, and with a cross product we want to put a cross between the vectors. And we're kind of these visual people. We see a cross, it's a cross product. We see a dot, it's a dot product, and that's it. Now sometimes this dot product, like you might have used these different brackets around it and such. In computer graphics I've rarely seen like these brackets used. It's just usually dot between them, and you have to know that these are vectors, and because these are vectors, then this dot is going to be a dot product. Now over here we can see that these are, well, numbers, because they're the lengths of vectors, and the cosine also is a number, so those dots here are just multiplication signs, like regular numerical product. But here it's this vector operation dot product, because it's between vectors. So from this video you should now understand different points and vectors. So we have locations that we call points, and we have directions that we call vectors. If we define different operations between them, namely addition, then this will lead us to this affine space where we have points and vectors in the same space, but the origin of those vectors is like there is no origin there. A same vector can be anywhere in this space, but points define the locations there. Now you have also seen some parametric geometry. So parametric line and parametric triangle equations. And this will become useful later on when we're trying to do ray tracing, for example. But now just know that if you take a couple of points or a vector and a point, or maybe you need a few more vectors if you want to do a triangle, then you can make a parametric equation where you input different real numbers, you get points on the object, different points for different numbers. We saw convex combination and pericentric coordinates. And we also saw some vector operations, and normalization is something you will need very often. Dot product is very useful and you will need often. Cross product you won't need that often, but it's useful to understand how does it work, and well, we will use it later on, but it's not that important if you don't remember this by heart, as long as you know normalization and dot product by heart.